So how do we make sure our logistic regression model is accurate? Well, to do that, we need a cost function. You might remember that for linear regression, we use the squared error cost function, which produced a convex curve like this one over here, and we'd iterate through our data points until we reach parameters w and b that minimize our cost function. So we would reach this minimum point over here. But if we were to apply the square error cost function for logistic regression, which is the model we've been talking about in module 3, we'd actually get a non-convex curve, which is this wavy curve over here. And in a non-convex curve, you have multiple minimum points. So this is a minimum point over here. This is a minimum point over here. But we actually want to reach the global minimum point because that means our cost function is minimized to the fullest extent at the global minimum. These points over here don't actually minimize the cost function completely. So that's the problem with applying the squared error cost function for a logistic regression. So to prevent this, there's actually a different type of cost function for logistic regression specifically. So for the squared error cost function, there's a loss term, which is like this value over here, which basically tells you how far the predicted output from your model is from the actual data point. So for the cost function for logistic regression, we'll define a new loss term that takes in our prediction of the learning algorithm, f, and the true output, y. So L here, our loss, is a function of f and y. So, and these will be our parameters for the cost function for logistic regression, because the loss term here, we can also pretend like that's our cost function. Okay, so what does the logistic loss function actually look like? So it is a bit more complicated, but not to worry, it's not that bad once we break it down. So there are actually two parts to the logistic loss function, and it depends on what the true value of y is. We talked about how in binary classification, there can be two possible values for y, 1 or 0. 1 means that whatever you're looking for is present, and 0 means whatever you're looking for is absent. So f is the output of logistic regression, and it's always between 0 and 1. So we're either going to use this function over here, right, on this line, or this function over here on this line, because y is either going to be 1 or 0. So let's look at the graph of the cost function when y is 1. So you can see that it's a negative log function. Okay, so the log function is the green line here, but remember, we want the negative log function, so we can depict that by reflecting our regular log function over the x-axis. So now we have negative log of f. And yes, it'll intersect the x-axis at 1. But it's also important to remember that f is the output of logistic regression, and f is going to be our x-axis here for the cost function. And f is always between 0 and 1. So the true value is going to be 0 or 1, but our model will output something between 0 and 1. So in that case, really only everything on the left side is significant to us. And remember, the green line is just a regular log function, so we could ignore this. So really all we're looking at is this red line over here. Okay, this is the only part we care about because it's to the left of 1. And also, remember that this is an asymptote because it's a log function. So if we zoom in here, we can really see what our cost function for logistic regression looks like when our true value of y is equal to 1. So remember, this is an asymptote. And say we had a data point over here on our cost function. Well, our cost in this case would actually be pretty high because our model, let's just say our model, that means our model predicted something like 0.1. It's pretty close to 0, right? And remember, this cost function is for the case when y is actually equal to 1. So 0.1 is very far off from 1, which makes sense because, look, our cost function is pretty high here. Remember, the cost is on the y-axis, okay? This is our loss function. It's on the y-axis. So it's outputting a pretty high cost because our output is far off from the real output. But the loss is lowest in this case when our f function outputs something that's close to the true label y. So if we had a data point that was closer to 1, our cost would thus be less. So as f outputs something closer to 1, our loss approaches 0. Now let's look at the other part when the true value is 0. So this part now. So when I graph negative log of 1 minus f, remember this is just really f, right? It looks something like this. And we just talked about, remember, our model will only output something between 0 and 1. So really only this part is significant to us. So if we zoom into it, we can see our cost function for logistic regression when the true value is 0. Our cost function is going to look like this. And you can see that, hey, when our model predicts something that's close to 0, say a point like over here, our cost is pretty low. Whereas if we predict something closer to 1, our cost is exceptionally high. Remember, this is an asymptote, so this goes on forever. So in this case, as our model outputs something closer to 0, our loss is closer to 0. Whereas the further the prediction f is from our target, the higher the loss. So like this point over here has a pretty high loss because it's far from 0, which is the true value in this case. Okay, so to summarize, remember that when we're computing our costs, we use summation. Remember this notation over here, summation. And this is used because we want to iterate through all the training sets, right? We want to compute the cost for every data point. So that means sometimes we might use this cost function when the true value for a specific data point is 0, and for other data points where the true value is actually 1, we'll use this cost function. So we're actually using like 2 separate graphs here, and then we add that all up to compute our final cost. And remember, the final goal is to minimize our cost. So once we get parameters that minimize our cost, that means our model is doing well at predicting values. And one thing to note is that, remember how we were talking about for the squared error cost function when applied to logistic regression, we'd have a non-convex graph? Well, when we apply this cost function, this actually turns out to be a convex graph. Proving this is beyond the scope of this module, but now that it's a convex graph, we can be pretty confident that we can reach a global minimum. And if we reach a global minimum, that means our cost is pretty low, which means our model is doing really well. Okay, I hope you guys enjoyed that video.